only in 1970. This compound could be made very easily through a precipitation process involving iron and hexacyanoferrate. And you have here two extreme structures of the Prussian blue presenting regular lacunas of the hexacyanoferrate moieties, or with monocations inserted into the tetrahedral sites of the structures. So as examples, Prussian blue has been used first in paintings, then dyeing of textile, in a photography process called cyanotype, as an electrochrome for radioactive cesium or thallium decorporation, for radioactive cesium decontamination of grounds and water, and also more recently as a material for batteries, which shows the strong applicative aspect of such compound. So at the very beginning of this century, studies started to be dedicated to the synthesis of Prussian blue and Prussian blue nanoparticles analogues in microemulsions, which was the beginning of a new era in the research dedicated to Prussian blue, with now hundreds of publications dedicated to the synthesis and use of Prussian blue at the nanoscale that will be the subject of my presentation. I will address the work we develop in my group in the synthesis, characterization, and use of Prussian blue and its analog nanoparticles regarding three different aspects: their porosity, their interface when they are associated with another component, and their composition, starting with the porosity. So as I've already mentioned, there are two kinds of sites accessible within the Prussian blue structure. The tetrahedral sites of the structure that can host monocations, or due to lacuna of the hexacyanoferrate, the presence of channels in the structure, which allows the incorporation of organic molecules. It is noteworthy that even if we can favor one or the other of these extreme cases, most of the time, the Prussian blue or its analogues nanoparticles that we are handling are in an in-between situation with both regular lacunas and monocations. The first example from our lab that I will show you uses the ability of Prussian blue to trap radioactive cesium. So exposition to radioactive cesium is harmful, and solution to speed its excretion are needed. The actual treatment consists in using Peros capsules of Prussian blue under the brand name Radiogardas. With a company developing a specific oily formulation, we developed the in situ formation of Prussian blue nanoparticles, as shown here. You have some examples of the different formulation tested, showing that in the most favorable case, we can obtain very stable colloidal solution with times up to 90 days. Sorry. So these formulations were then tested on mice for the excretion of cesium. So the groups GHI were treated with an increasing amount of Prussian blue in the oily formulation, and compared with groups C, D, E, F that were treated with increasing amount of Radiogardas. Group B was treated only with the oily formulation without Prussian blue, and group A treated with water only. So you can see that there is a clear increase of excretion through the feces that can be seen for the formulation of Prussian blue compared to Radiogardas with, in the most favorable case, a factor 4, and with a clear dose effect for the formulation that cannot be seen for Prussian blue. So such formulation can be administered as a spray, and the results obtained for the increased excretion of cesium, the dose effect that we can see, and note shown here, the efficiency to remove cesium from the heart makes the formulation particularly attractive to treat babies, children, and teenagers that may be exposed to radioactive cesium. So now I'm switching to the overporosity made of channels due to the hexacyanoferrate lacunas. We can use such porosity to trap organic molecules. Here is an example with aminoanthracene and rhodamine B. Those molecules are well-known fluorophores. So working with biologists for different studies, we needed to have luminescent Prussian blue nanoparticles to locate them in the cells. So this is the initial reason why we developed this work. Here you can see solution of Prussian blue nanoparticles, and Prussian blue nanoparticles where we trapped aminoanthracene and where we trap rhodamine B, and you can see here their fluorescence. Through modelization, we can locate and identify the interaction of these molecules within the structure. And here you have the final results showing that we can locate these nanoparticles within cells, either using the luminescence of aminoanthracene or using the luminescence of rhodamine B within the pores. We can also use these channels to introduce organometallic compounds such as this one here that will decompose to give silver alloy nanoparticles. In this case, we're using a Prussian blue analog, which is made of nickel and chromium. And so you may visualize here on this image, on this transmission electron microscopy image, one of these Prussian blue analog nanoparticles, and all the tiny dots that you can see here corresponds to the gold-silver alloy nanoparticles. And such nanoparticles can be used for 4-para-nitrophenol reduction in the presence of borohydride. So using the Prussian blue analog alone, an induction time is needed that can be due to the lack of hydrogen generation from the borohydride via the Prussian blue analog at the beginning. This induction time can be indeed suppressed by adding hydrogen in the solution before adding the borohydride and 4-para-nitrophenol. However, in both cases, with or without hydrogen, it takes 13 minutes for completion of the reduction of 4-para-nitrophenol in our conditions. When adding the silver gold alloy nanoparticles into the Prussian blue analog nanoparticle, there is a clear boost of the catalyst performance due to the beneficial interplay with a reaction which is completed in only 8 minutes. And adding irradiation with white lead allows the reaction to be completed in only 6 minutes. So lead irradiation is believed to increase the diffusion rate of reactants in the solution due to a rise in the local temperature around the metallic alloy nanoparticles. So this example makes a perfect transition to address the interface interplay that may happen when considering nanohybrids involving Prussian blue or its analogs as one of the components. So this example here is a simpler version of the previous one with a single metallic nanoparticle gold surrounded by a Prussian blue analog, which is made of a Prussian blue analog of nickel and iron in that case. So here you have the transmission electron microscopy images of these core shell nanoparticles. And as you can see here, we can remove the gold core in order to obtain hollow Prussian blue analog nanoparticles. This is what you can see on this transmission electron microscopy image. Or we can also grow a second shell of another Prussian blue analog, for example, nickel chromium. And you have the formula here with gold at the core, the first shell made of nickel iron Prussian blue analog, and a second shell made of nickel chromium Prussian blue analog. So this method can be used varying the first shell of the Prussian blue analog for compounds named A1 to AG, for which you have here the transmission electron microscopy images. But we can also modify the thickness of a second shell made of nickel chromium for compounds 3A to 3D, and we can, for 3E, for example, change both the shell thickness of the first shell and the second shell. So now we can follow the influence of the shell thickness on the plasmon resonance band of the gold nanoparticle. I show here the results for the core shell nanoparticles with a double shell, with 3A from 3D, where we're modifying the thickness of this second shell only. And in this case, we have another thickness for nickel iron 2. So a progressive redshift of the lambda max of the surface plasmon resonance band from 520 nanometers and to 552 nanometers, that is reported here, as a function of total thickness is observed. This can be due to the change of the refractive index of the shell relative to that of water and the presence of a saturation beyond a shell of thickness of 15 nanometers caused by the scattering effect. The optical properties of the core shell nanoheterostructures thus depend on the shell thickness. However, it also depends on the Prussian blue analog nature, as the effect is more pronounced for the double shell structure that I'm showing here compared to the other example I mentioned where we have only one shell of nickel iron Prussian blue analog. Regarding now the magnetic properties for the magnetization versus temperature, the maximum temperature for these curves increases linearly as the shell thickness increases, then tends to saturation for larger shells, suggesting a change in the magnetic regime of the nano objects from the shell thickness of 7 nanometers. The profile of the curve indicates that the critical shell thickness is situated at 7 nanometer for this second shell of nickel chromium. And the transition at 7 nanometers in thickness corresponds in fact to the frontier between a monodomain situation and a multi-domain situation. So this model example thus clearly demonstrates the effect of the interplay between the two components of the nanoheterostructure, both on the optical properties of the gold core and on the magnetic properties of the Prussian blue analog shells. Now, instead of wrapping gold nanoparticles with Prussian blue or its analogs, we also investigate the situation where the growth of Prussian blue is made on a gold surface. We can use bare gold or cysteine, functionalized one. And the AFM images here show clearly that the amounts of precursors allows to increase the covering of the surface in both cases, but the presence of the amine function definitely permits a higher coverage density. Also, it should be noted that the Prussian blue nano objects obtained have a pyramidal shape for low concentration of precursors, while more cubic for high concentration. That can be seen as a variation of the synthesis kinetics. We can also grow Prussian blue nanoparticles on a glass slide covered with a lipid bilayer. So depending on the lipid bilayer composition here and the concentration of reactants, as you can see on this AFM image, the coverage density can be modified. The presence of a cationic charge in the lipid bilayer favors the coverage density. So as in the previous case with the amine, when we're favoring the interaction between the surface and the Prussian blue precursors, this is the key to obtain a high coverage. So Prussian blue is a very appealing agent for photo-induced generation of heat. As you can see here, irradiation with a laser in the near-infrared region of one of these surfaces allows to obtain a fast temperature increase of the surface without any fatigue of the material, and which is only dependent on the power density of the laser. So we can play with this property by modifying the composition of the Prussian blue, which is the last part of my presentation. We synthesized a series of Prussian blue nanoparticles with an increasing amount of manganese, up to 33% of added manganese. The structure remains the same, cubic, while the lattice parameter increases. However, above 33% of manganese, we do not have anymore the cubic structure of Prussian blue with inserted manganese, but we have the monoclinic structure of the manganese iron analog. So we will concentrate now on this series of compounds up to 33% of manganese. If the manganese can substitute the iron in the structure, here, substitution of iron free in the structure, or it can be trapped in the tetrahedral sites of the structure. So performing infrared spectroscopy completed with a modelization, which we were able to confirm that the first case, substitution of iron by manganese in the structure, is the actual situation, which is also coherent with the observation of a lattice increase here, as the manganese element is bigger than the iron one. Now, here we are checking the influence of the presence of manganese in the structure on the photothermal properties of the Prussian blue. You can see that we have a clear batrochromic shift when adding manganese in the structure. So this should favor the photothermal properties, as the adsorption maxima is coming closer to the wavelength of a laser used for the irradiation in the near-infrared region at 808 nanometer. However, increasing the amount of manganese to a certain point decreases the molar extinction coefficient. So the origin of the absorption phenomena in Prussian blue is due to an electron transfer between iron at oxidation state +2 and iron at oxidation state +3. Increasing the amount of manganese leads to a decrease in the number of possibilities of electron transfer, and thus a decrease of the molar extinction coefficient. So the resultant photothermal properties that you can see here are thus a balance between the batrochromic shift and the molar extinction coefficient. This leads to a better photothermal efficiency when increasing the amount up to 10% maximum, and then we observe a strong decrease. So we have used 3 types of nanoparticles to eradicate cancer cells: Prussian blue with a low amount of manganese, and Prussian blue with a high amount of manganese. And you have here the corresponding transmission electron microscopy, the absorption spectra. You have here the eradication of the cells immediately after irradiation for the 3 types of nanoparticles. So Prussian blue with low amount of manganese, Prussian blue with high amount of manganese, and 24 hours after irradiation. And you have here the corresponding graph. So you can see that for Prussian blue and Prussian blue with a low amount of manganese, after 24 hours, we obtain almost the same amount of dead cells. The important thing to notice is that for the Prussian blue nanoparticles with a low amount of manganese, we already observed quite large amount of dead cells immediately after irradiation. For the nanoparticles that contains a high amount of manganese, however, we do not observe this effect immediately after irradiation, and after 24 hours, the efficiency is less important than Prussian blue or Prussian blue nanoparticles with low amount of manganese. So definitely the Prussian blue nanoparticles with low amount of manganese are the most efficient, which is perfectly coherent with what we've seen regarding previously the photothermal properties of these three kinds of nanoparticles. So as we've seen that Prussian blue has a porosity, we can use such to load with doxorubicin, which is an anti-cancer drug. And here you have the eradication of the cells only using irradiation without doxorubicin, here only with doxorubicin without irradiation, and here with both irradiation and doxorubicin. And the different colors here correspond to before irradiation, when there is an irradiation, or 24, 48, and 72 hours after. And we can clearly see here that when we have both irradiation and doxorubicin, we have a clear better efficiency of the nanoparticle, which is confirmed by the combination index calculation, which is inferior to 1, which shows that there is really an additional value of the combined treatments. So I would like to thank now people from my group. So Julia Larionova, Saad Sen, and Gauthier Félix. Julia, she's a physicochemist. Saad is a chemist, and Gauthier a physicist. And the PhD students that made the work, so Jiang and Go working on the deposition of Prussian blue on surfaces, Guillaume Morin working on the core shell nanoheterostructures, Ekaterina Mamontova, who performed the work on organometallic and organic molecules loading in Prussian blue nanoparticles, and Maël Cahu, who performed the study on manganese-containing nanoparticles. And finally, I would like to thank you for your attention.
Talk is open now for question answer session, please. No questions?
Thank you, Dr. Gauri, for excellent presentation. I have a question. I'm Professor Varsha Baveja. I have a question. Can we use this luminescent Persian blue to study developmental stages of any embryo?
Sorry, can you repeat just the end of the question? I did not hear it.
Can we use this luminescent Persian blue to study developmental stages of any embryo?
Well, that's a good question. We never thought about that, really. It really depends if the nanoparticles will be incorporated in, but if it's the case, yes, I guess so. It will depend on the location of the nanoparticles. I'm sorry, but I'm not really a specialist about embryo growth, so I do not know how it proceeds exactly, but if the nanoparticles can enter, yes, probably.
Basically, I just want to know whether this is safe or not. Is it toxic?
No. Is it toxic or not? No, it's not toxic. We did a lot of cytotoxicity studies that I haven't shown here. Maybe I'm showing, yes, sorry. I've shown that here, for example. You see when you're looking at the nanoparticles that contain sorry, I need to add the pointer. When you're using here Prussian blue nanoparticles with only 5% of manganese, which are the most efficient in terms of photothermal efficiency. Here, the blue curve, you see that there's no toxicity. The cells are growing normally. We have toxicity only, of course, if we add doxorubicin, which is normal. We always have a leaching of doxorubicin. But the nanoparticles, they are perfectly safe. We did a lot of studies in vitro and in vivo, also on mice, but I haven't shown here. And very recently, there was a nice paper that showed that, in fact, when the Prussian blue nanoparticles are stable for 24 hours, and then they start to decompose to give iron hydroxide, which is not harmful, and hexacyanoferrate, which is not harmful too. Hexacyanoferrate is even an additive that you can find in food. So there's no identified toxicity for Prussian blue nanoparticles, even the one that contain a low amount of manganese.
Okay, thank you.
Do we have more questions, please?
Sir, this side Dr. Ruchika Joshi from Physics Department. I have a query. As you have written that anti-cancer activity for of DOX loaded into DOXMN 5%. So have you done some research over it, like as you are giving guarantee that it is anti-cancer activity? Do you have literature supporting thing related to this, sir?
Sorry, you mean about the use of doxorubicin?
Yeah.
Oh yeah, doxorubicin is a very well-known anti-cancer drug that is used even for human and which is approved. So yes, there is a clear effect of doxorubicin as an anti-cancer drug.
Okay. Thank you, sir. Thank you.
Any other question, please? If no more question, then thank you very much, Dr. Gauri, for sparing your valuable and precious time for this international conference on integrative chemical science for health and environment, ICHE 2023 in hybrid mode, organized by Department of Chemistry. The talk on nanoparticles and their analogs for innovative applications was highly informative, fruitful, and reviving for all of us. We hope to hear you again, sir. Thank you very much.
Thank you very much to you.
Thank you.
Now we welcome the second speaker. I, Varsha Baveja, welcome Professor Digamba Patra. Professor Digamba Patra is chairperson of Department of Chemistry.
Hello, yes. Good afternoon.
Okay. Yeah, good afternoon. Professor Patra is chairperson of Department of Chemistry, American University of Beirut, Lebanon. Professor Patra is working as professor and chairperson in the Department of Chemistry, American University. His area of research is nanochemistry, optical biosensing, biophysical chemistry, fluorescence spectroscopy, and imaging. He is an active member of many academic societies such as Asia Pacific Chemical, Biological, and Environmental Engineering Society, Biophysics Society, AVH, member of German Chemical Society, and many more. He has guided many PhDs and graduate students. He is recipient of many awards and distinguishes. Professor Digamba been involved in many editorial boards of renowned journals and has also published a lot of articles in reputed international journals. So Dr. Patra, I welcome you to speak on tuning hybrid nanoparticles with properties for biomedical and analytical applications. So over to you, Dr. Patra.
Thank you, Dr. Ghosh, for your kind introduction. I am audible. Can you hear me?
Yes, sir.
Yes, clear.
I first thank the organizing committee and Professor Dr. Kumari for inviting me to give this talk. I could not make it because this is the semester time and it's very difficult to get leave during this semester. So I had to apologize for not being in person, and I will give my presentation, as you know, through the online mode. So today I will be sharing one part of my research where we focus on curcumin-based nanoparticles, especially metallic nanoparticles and nanohybrid particles for health and environmental application. So when I talk about curcumin, I think almost all the audience are aware now the curcumin, the turmeric powder is widely used in spices and in pharmacology, and now they also use as additives or supplements in this is a growing market in Western world. In Indian market, all of us know very well, it is quite popular. But in Western market, it is exponentially growing. The supplement market is about more than $125 million, and it will keep growing in. And recently, Indian government also specially made a board for turmeric. So my approach here is how to take other scientific advantage of these spices. And these spices consist of a molecule curcumin, and this is the molecule as I show you here. And this molecule has many applications in medicine and cosmetics. So my focus is something slightly different. I am exploiting not only the medicinal properties, but also the chemical properties. So to talk about, when we talk about environment, the most important part today is how to make the green synthesis. Means green synthesis we are talking about means how to make chemicals that we use in the lab or in industry that is eco-friendly or biocompatible, or we can, at least if we cannot avoid, then minimize the use of toxic reagents. And one way of doing is, whatever the reaction we are doing, instead of using a toxic reagent, we can use environmental friendly chemicals to do it. And in that line, my idea is to use curcumin as a probe molecule, which is a safe molecule, quite well known in the literature. 8 grams of curcumin one can take every day, and still it is not toxic. And it is also can be, it can work as a green reducing agent. So I will be talking about these ideas, so little more in details. So first thing, before I go, I would like to give some hints towards the nanoparticles that I am interested. As you know, nanoparticles means people can go from 1 nanometer to 1000 nanometer, depending on what they emphasize. But largely, people agree that 1 to 100 nanometer is where the focus is. And my work is between, I focused from 10 nanometer to about maybe 800, 900 nanometers. So we can prepare nanoparticles in many different ways. One, just using only pure metal, or we call metallic nanoparticles, or we can make organic based nanoparticles, which is carbon based nanoparticles, or lipid based nanoparticles, polymeric based nanoparticles, and other inorganic based nanoparticles include semiconductor, ceramics. So I work in the gray area where I combine metal nanoparticles, lipid nanoparticles, and polymeric nanoparticles for various applications. So the interesting part of nanochemistry is when you tune the nanoparticles in different size, you change the properties. Not only that, the shape itself can change the property. And some of the examples I'm going to discuss today, like if you have nanorods, a small length, about 100 or few micrometer, or you can go to nanowires having longer than micrometers. You can have sphere, you can have nanoflowers, nanoprism, different kinds of shape you can have, and that can influence the chemical properties. And thus we can have different application from this different size and shape of the nanoparticles. So one of the most popular one, people know this is one of the gold nanoparticles, where you can tune gold nanoparticles in different color depending on the size. As you see, from 30 nanometer it was red, then you can go to really violet color and 90 nanometer, but you can tune. And 2 days ago, as you know very well, the quantum dots got the Nobel Prize in chemistry, and they are also, you can play around. We have worked also some of the nano quantum dots, but I will be not talking today. They are also, we can manipulate the size of the nanoparticles and change the optical properties. So one thing when we prepare the metallic nanoparticle is the main challenge is how to stabilize it. The chemistry, nanochemistry was not developing because when we were preparing metal or particles, the particles were not getting stabilized in the nanometer region. So one way of doing is to modify the surface of the nanoparticles with different organic or inorganic ligands. And this is where we can manipulate the size. So how, based on the synthetic procedure, there are many ways. You can do physical method, you can do chemical method, you can do biological methods. So today, when we will be focusing, we will be talking about something, this surface modification, where we have a nanoparticles and we modify the surface and we tune for different applications. So when we use the curcumin, the one of the first paper we published on curcumin is how to prepare a gold nanoparticle using curcumin instead of toxic reagent, which are well known in literature. Like in literature, they use sodium borohydride, they use citrate. Citrate is not toxic, but it can lead to a toxic application later on. So we replace one of the well-known chemicals. Instead of sodium citrate, we replace with gold. We replace with curcumin, and then we prepare the nano rods. This is one of the first where we showed that we can selectively synthesize nanorod by modifying the chemical procedure with curcumin, and we have surfactants like CTAP and others. Then we further progress, and what we did, we completely avoid any chemical and just we use curcumin to prepare gold nanoparticles, and along with gold we add some silver to prepare nano wax. So here it's a one-pot synthesis, so we don't need to have long procedure. Just in one pot you put everything and then you synthesize the nanoparticle depending on the condition. And what we found, when we have alkaline pH or extreme pH at pH 13 above 60 degrees Celsius, we could able to get the nano waste. And this nano waste we applied for various applications. So one of the application I will be talking about is the application in environmental degradation of toxic chemicals. So this is where we have different size. As you can see, we can completely get very nice nanowares using our method. And these nanowares we use to reduce para-nitrophenol to para-aminophenol. And this is one of the most standard application in chemistry, where we try to reduce toxic chemicals to less toxic chemicals. And what we found is, instead of using nano particles, then if you use nanoweights, the reduction potential is very high. Almost it can go in many folds. So this is one of the first application we talk about, the nanoweights. Then we also use nanoweights for optical sensing. The same nanoweight we tried with resonance relay scattering, a method where you collect the scattering at the absorption as well as the emission band. And what we found, the nanoparticles, gold nanoparticles has scattering signal, but when you make it gold nanoweight, the signal is enhanced. The signal is enhanced means we can increase the sensitivity of a target species. And in this case, we optimize various conditions and we measure the vitamin E. Vitamin E is associated with sterility, reproduction. So the chemical associated with is topopherols. So we selectively could sense topopherol using the our gold nanoweights. So I will not go in details. I will also discuss some other application what we can do using such nanoparticles. Then instead of using gold nanoweight, we came back to the gold nanoparticles, and we modified the surface with a surfactant called F108. It's a polymer, and we also compare with CTAP functionalized, a surfactant. Then what we found, if we take CTAP, there is no change in the signal for glucose when we add glucose. As you know, glucose sensing is very important for medicine, and we then modified with F108 functionalized particles. And what we could see is we can detect glucose that is relevant to our biomedical application, like for clinical. In the same range, we could estimate it, and we could propose a mechanism how this our gold nanoparticle could able to aggregate in the presence of glucose and improve the signal. And we can measure all kinds of different kind of glucose, and we compare with the enzymatic acid. So then we also targeted other species. So we, instead of, because most important thing in bioanalytical application or biological application is when you are designing a sensor, the sensor should be selective. When you use the real sample, then you should not have other background signal, and we should not have interference from the other molecule. So we targeted for ATP. One of the idea is then what we did, we use a gold nanoparticles prepared using curcumin. Then we attach with a host molecule. Curcubit uril is a pumpkin-shaped molecule similar to cyclodextrin, if some of you know. It's a curcubit uril and it is a host molecule. So we attach this molecule with gold nanoparticles, and then we use a fluorescence probe, in this case rhodamine B. Rhodamine B binds with curcubit uril and its fluorescence signal is enhanced. Then we change for different triphosphate like ATP, CTP, and GTP. And what is interesting is what we can do is selectively we can recover the fluorescence in the presence of ATP. That means we can develop a sensor that can sense only CTP, not GTP, UTP. Normally, these are the common interference, and people use aptamers, DNA based, which are very expensive to selectively determine ATP. So in a very easy method, we could estimate ATP using our method. Then we also work on other kind of nanoparticles like copper-based nanoparticles. So we did copper-based nanoparticles for example, for destroying methylene blue, like textile industry use all these kind of dyes, and they pollute the environment, especially the water, natural water, sea level, and it also pollutes especially rivers and all the groundwater. So how to degrade them? So one of the challenge is to develop a better catalyst for degradation of methylene blue. So this is a very, I think, demanding problem in chemistry and chemical engineering. Many people work on methylene blue. So normally gold and silver can be used, but these are, as you know, they're a very expensive material. So we use a curcumin-based copper oxide, curcumin conjugated copper oxide nanoparticles. And these nanoparticles we prepare in different shape, like I mentioned earlier, and we made nano grains, like it looks like a grain, like a wheat or rice grain. And we compare with the smaller nanoparticles. This is how methylene blue becomes from color to colorless after the reduction. So we use copper oxide nanoparticles as a catalyst, and we could improve it, especially the nanograins are much more efficient for reduction of methylene blue compared to copper oxide nanoparticles. So this is some of the technical data I can say. So as you see, nanograin has more efficient in reducing methylene blue. So we study in details kinetics and other parts, which I will not discuss now. Then we use also similar nanoparticles, curcumin-based copper oxide nanoparticles for estimation of cysteine. Cysteine is one of the important assay for the biological samples. So here we can selectively estimate cysteine. Even we can do for homocysteine, and there is no interference from other analytical species, especially potential amino acids and other samples. So then we did a similar assay which we did for gold nanoparticles. For copper oxide, we use a method where we want to do assay for dopamine. As you know, dopamine is responsible for depression, and there is significant level of dopamine one should have, and always in clinical practice people estimate the dopamine. So in this case, what we did, instead of using gold nanoparticles to have dopamine assay, we use copper oxide nanoparticle along with curcumin, and we use curcubit 6 uril. As you see, the size of the host has been decreased, a smaller size, and we also change the probe molecule to acridine orange, so that we can selectively, even the ATP doesn't interfere. This is the idea. So Then we could able to do a similar method here using fluorescence resonance energy transfer. No, sorry, in this case, not fluorescence. This is the fluorescence quenching of acridine was recovered in the presence of dopamine. Thus, we can selectively, as you see, the signal can go up to threefold. Dopamine, we can estimate the dopamine. We also tried some of the green synthesis where we don't use any other solvent or any other chemical except the nanoparticle to accept silver and curcumin, and we use solid phase, we grind it and we prepare nanoparticles. And these nanoparticles were used for reduction reaction.
No, ma'am, हमारे यहाँ से तो इंटरनेट कनेक्टिविटी सही है.
So these nanoparticles were tested having different sizes, and we could able to reduce different organic species. These are the mechanism. So I'm not going into detail. So then I will go to the second part of my talk very briefly. Instead of using metallic nanoparticles, we can use also nano. Can you please pause? Okay, so now here what we do, we use polymer to prepare polymeric based nanoparticles like poly-L-lysine or different kind of. Here we use a cationic polymers, and these polymers aggregate in a certain conditions. And in the presence of curcumin, we dope the curcumin inside. That means we encapsulate within the polymer curcumin, and then we look for the improving selectivity. For instance, if you take curcumin doesn't selectively, very slightly it increases for guanine. And if you have curcumin for silica, the signal change is almost negligible. But if you change to nano capsules like we have prepared in the presence of curcumin, what we see, the signal for guanine is 5-fold enhanced, whereas other nucleobases are not affected. That means we can selectively assay a particular nucleobase using our kind of nanoparticles. And these are important for DNA sequencing. In DNA sequencing, you need to identify each nucleobase separately. So such method can be useful. Similarly, like cholesterol, as you know, cholesterol estimation is very important in life. And curcumin-based nanoparticles we prepare using, again, another kind of polyelectrolyte. And these polymers, like cationic polymer, we prepare the nanohybrid particles. We call it because we have some silica nanoparticles along with curcumin and polymer. Since there is organic, inorganic material, we call it nanohybrid particles. And these hybrid particles, what I will say, if you look at curcumin alone and curcumin or cholesterol, there is an enhancement in signal. But if you add curcumin-based nanohybrid particle, still you have an enhancement. But this enhancement is much more higher than in the presence of curcumin. Okay, this sensing part is okay, but what is most important is if you look at the selectivity, curcumin fluorescence is quenched by mercury and copper metal ion. But if you take our nanohybrid particles, where also we measure the fluorescence of curcumin, these nanohybrid particle signal is not affected by all the metal ions. That means we improve the selectivity. Now let me go for some of the biological molecules like BSA, bovine serum albumin, is very common. It highly influences the signal of fluorescence signal of many molecules, including curcumin. Look at the curcumin signal. The curcumin fluorescence increases in the presence of BSA. But if you use our nanohybrid particles where curcumin is encapsulated, the signal doesn't change. The signal changes only when you have cholesterol. So that means we can selectively estimate cholesterol even in the presence of BSA, oleic acid, and palmitic acid, and all these chemicals, which could interfere for curcumin alone. So we can improve the selectivity as well as the sensitivity by preparing such nanohybrid particle-based curcumin. So now this is for cholesterol estimation. So the recovery was good. Then we also did some from polymer-based curcumin nanoparticles for photodynamic therapy, like especially for anti-cancer activity. So we use this kind of polymers to prepare curcumin encapsulated nanoparticles, and here is the data. So as you see, the ICHE-50 is the, most of you know, maybe for chemists, the minimum concentration you need to kill the 50% of the cell. So if you compare the curcumin about 49 micromolar. And if we use our curcumin-based nanoparticle, this concentration reduced to 1.8, almost you can see, or 2. So 2 and 50, roughly 25-fold less concentration. So if somebody is eating, let us say, 50 milligram, then he needs to just eat 2 milligram to have the same effect. And this is in the presence of dark, means it is only for normal, how many. Then when we put light, that means for especially for photodynamic therapy, this kind of application, then look at here, in the light was 49, in the dark it was 150, so almost 3 times less. So same thing, it was 4.4 in dark, and the light 1.8. So that means these molecules has the potential for killing cancer cell. And as you know, curcumin is safe, so we did not do in this case the test for the normal cell, because we just took the help of the literature. So then we also did another experiment. It is quite known in traditional medicine that when you take curcumin along with pepper, black pepper, the bioavailability is very high. So we wanted to test it. So we take curcumin from the turmeric and piperine from the pepper, and we tested it, and we compare their encapsulation efficiency, drug loading, all of them improves in the presence of piperine. So that is first. Second, when we test their release kinetics, and we really got a good release in the presence of piperine. The release of curcumin to the cell improves in the presence of piperine. And then the killing of cancer cell also much better. Especially here we made experiment on this is for, I think this is breast cancer. No, I think this one we did for the colon cancer, so Kako cell. So here, what we see, the bioavailability is improved, as well as the anti-cancer activity of curcumin is much higher in the presence of piperine than curcumin alone in the nanocapsule. So we also did some anti-scavenging studies. So since I will have not much time, so I will just summarize that how we can. I will show the last slide. So if you prepare different size nanocapsule, then what we can do is, by making this different size nanocapsule, we can control the release. For instance, here, if we have different nano size, the release is controlled, as well as the antioxidant activity of curcumin can be controlled by making the different size polymer nanoparticles. So this is Beirut. So where I am, my university is this one. This is our campus. So it was one of the 8 beautiful campus in a ranking few years ago, and in another ranking, in modern ranking, it was 23. So I thank my collaborator, Professor Bedun, and also my students, my research associate, Riham, and all my students who work on this project. Thank you very much.
Thank you, Professor Patra, for the informative talk. So with your due permission, can we have some questions? Can we take some questions?
Sure, sure.
Audience, do you have any questions?
Dr. Patra, myself, Dr. Kamna Singh, I have a question. As you discussed about curcumin-based nanoparticles in your talk, can we use these nanoparticles for other herbs also, like ashwagandha or like others, or they are specific for curcumin only? These nanoparticles.
one needs to test these nanoparticles, for ashwagandha, what is the chemical it is present in ashwagandha, we need to test it. So basically, I have focused in curcumin because curcumin has fluorescence properties, it absorbs in visible region, so it becomes easier for analysis. But of course, also like piperine we had tried, and there is eugenol we have tried, but yes, I think it needs to be tested. This is in the same line, for other chemicals, especially people that use in the Ayurvedic and other kind of traditional medicine. Those molecules need to be tested. One of the thing, where the scientific community and especially people who work in naturopathy or Ayurvedic, there is a big gap. And the people who work in Ayurvedic, they never try to understand the modern technology, modern medicine, how it works. We approach in molecular levels, and they just take the mixture and they try, and often it doesn't work. The main reason it doesn't work is most of the molecule, even though they can help, they don't have good bioavailability. And the best way to improve bioavailability is to improve the delivery system, like we are doing for curcumin. So this is why I think curcumin market is also going up. Of course, I think that can be done.
Audience, any question?
Yes, may I ask a question? Yannick Gouari.
Yes, please.
Yes. I would like to ask a question about the beginning of your presentation when you synthesize gold nanorods.
Yes.
In that case, I do not clearly understand if you're completely substituting CTAB or if you're still using CTAB for the nanorods.
CTAB is never used to prepare. CTAB is always a conjugating agent in that case. The reducing agent was sodium borohydrate. So we take the seed method. So first a nanoparticle is prepared using sodium borohydrate or sodium citrate. Then these nanoparticles are grown to make nanorods using ascorbic acid. This is the standard method people follow in literature. So we did not use ascorbic acid, we use curcumin to prepare the nanorods in the first part of my talk. That is the first project. But now we are not doing anymore. We can completely avoid CTAB and citrate and just use curcumin and gold salt and prepare nanoparticles. But in the beginning, yeah.
You can obtain then nanorods, gold nanorods, without any CTAB on the surface at the end.
No, not nanorods. Recently, we have not worked on nanorods, but nanoparticles, yes. Nanorod we use, nanorod. Actually, we have proposed in this article, I think Journal of Physical Chemistry, we have published in that article, we have proposed two mechanisms. When you change from CTAB to citrate, you can actually control the yield of nanorods and go to nanoparticles. We have proposed the mechanism also, how it grows, different sites.
Okay, thank you.
Thank you.
Any other question? Okay. So thank you, Professor Patra, for very enriching talk on curcumin-based gold nanoparticles and other spices also, like you used piperine also, which has many biomedical applications, like treating various chronic diseases like cancer. I really astonished to see that you work on curcumin-based copper nanoparticle, which has wider application in textile industry. So it's really wonderful, and hope we sometimes in future we will get the opportunity to hear you in person. So on behalf of the team of ICHE Department of Chemistry, Deshbandhu College, I extend my sincere gratitude to you for delivering a beautiful talk. Thank you so much.
Thank you very much. I appreciate. Thank you for the invitation. Thank you.
Now, I stand before you today with immense gratitude and a healthful appreciation as we come to the close of this remarkable first day international conference event. It has been an honor to serve as your host and deliver this vote of thanks on behalf of our entire international conference college community. First and foremost, I would like to extend my heartfelt thanks to our distinguished speakers for gracing this occasion with their presence and wisdom. Your guidance and support have been invaluable in making this event a resounding success. Your willingness to lead and inspire our college community is truly commendable, and we are grateful for your time and commitment. A special thanks to our guest speaker as well as our chairperson and all those who contributed their talents and expertise to make this event both enlightening and entertaining. Your contributions have been added depth and color to our this conference, and we are grateful for your participation. Thank you all for making this conference a success. Now, I would like to request Dr. Harindri Chaudhary ma'am to give a token of thanks as a memento to our chairperson.
Professor Patra and Professor Gauri, the team of this team, conference team, has sent you an email, token of appreciation on your email. Thank you so much.
Thank you very much. Thank you.
Thank you. Thank you very much.